Hello everyone, welcome to the week 3 of the problem solving session for NPTEL analog computer networking class. So today we will be solving some problems based on the topics that have been taught in week 3 of NPTEL computer networks class. So first we will go through the chapters, go through the content of the lecture briefly, and then we will attempt to solve the problems. So with this I will be starting today's lecture. Let me share my screen. Yes. So today's topic will be space and time switching. So a brief about space switching and time switching have been presented in week 2, and now in week 3 we will be extending those topics and we will be exploring the possibilities of hybrid space and time switches. So first we will go through a brief about the space and time switching. So here time division switching means that when you have multiple packets that you want to send, you can send them slot by slot. So that is time division switching. So each time slot one data gets transmitted, then another user wants to send a data, then they will send in the next time slot. So one after another in one time slot after another, the data is getting shared. That is called time division switching. But in space division switching, for all users, there are specific lines or cross points. So here there are say n users and there are uh, n users in the input and m users in the output. So these n users want to communicate with any one of these m users, then there are dedicated cross point for each pair of input and output, and through that a link is established. This is called space division switching. But in time division switching, we send the data in a time slotted fashion. So here we can see there is a time switch. So in the time switch, if the frame 1 will come and frame 1 will be sent in the first slot, and then rather frame 1 will be divided into time slots, and the first data is sent first 1, then 2, then 3, like that. It is stored in the buffer. The entire frame is stored in buffer, and then they are transmitted according to their time slots. So now what happens is, if one frame arrives and their data is divided into slots, and the slots are getting transmitted one after another, and in that time another frame arrives, then the channel is busy. So if one frame only sends their data and other frames have to wait, that will create latency. So and the for the users that are waiting, so to give a certain amount of fairness in this system, so that each user can transmit their data in a relatively fair manner, we do a time slot interchange operation. In time slot interchange operation, what happens is, like, if one pair frames one slot is transmitted and the next slot might not get transmitted just immediately after, what happens is other frames might transmit. So in that time, that next slot of that frame has to wait, and when the time comes, then the next slot of the next frame will be again transmitted. Next slot will be transmitted. So here there is a data storage, and here we are sending these data, dividing into slots, and these slots are stored in the data, and when the time comes, data storage, and when the time comes, they are written out. So the frames are coming, they are written into the data store, and then they are sent when their time comes. So there is a read operation and there is a write operation. For each slot, there is a read operation and there is a write operation. Now the frames since we are taking voice communication here, so in voice communication the frames are usually of 125 microsecond duration. That is the industry standard for voice communication. The frames will be 125 microsecond duration. So if one read or one write operation takes, say, TC amount of time, if one read or one write operation, so here one, yeah. So here there is a data storage. the data is coming n data, so it is divided into slots. This is the ith slot, this is the jth slot. Now these are getting written here in the storage. So this is the ith slot data, this is the jth slot data. So these are getting written in the storage and then they are getting transmitted. So when they are getting transmitted, it might be that J is transmitted first, I is transmitted later. Might happen because of the traffic. So what happens is this is a in this way. So there is one read cycle here and one write cycle. So assuming read and write take the same amount of time, let read write operations take tc time. So frame, so how many slots do these frames need to be divided in? So each frame gets divided into so each frame is basically getting divided into slots. So each operation takes 2 tc time. So there is read operation which takes tc and then there is write operation which take another tc. So in each frame slots are of 2 tc duration. So the time needed to transmit the slots are 2 tc. So how many slots can you transmit? Number of slots is simply the frame length divided by 2 tc. So 125 by 2 tc, 125 microsecond by 2 tc. So where tc is also in microsecond. So this is the number of slots. So number of slots, or you can say number of channels. So these are the number of channels that can be supported by the memory switch. So 125 by 2 tc, where 125 is the frame time in microsecond for a 8 kilohertz sampled voice channel. So the from there, yeah. So now there are time switching stages inherently require some form of delay element, because all the frames do not get processed immediately as they come. They have to get stored and they have to they get delayed. So this delay is implemented using RAMs. So what happens is the data comes, they are stored in the RAM, and at a later time they are transmitted back. So the RAMs are in essence implementing the delay. So there are two basic ways in which the time stage memory can be controlled: written sequentially and read randomly, or written randomly and read sequentially. So basically, since this is a random access memory, so it is, both operations are not sequential. So either one of them have to be sequential. So we either read or write, one of them is done sequentially, but another one of them is done using random access. So this is the operation for RAM. So the second mode of operation, so the first mode of operation implies that a specific memory location are dedicated to respective channel of the incoming TDM link. So whenever there are specific locations, so whenever the data is coming, they are sequentially getting written. So when data is coming, they are sequentially getting written, but they are not getting read sequentially, they are getting read randomly. So the data is getting written in the storage sequentially, Data for each incoming time slot are stored in sequential locations. So as indicated, the data received during time slot 3 are automatically stored in the third location. So whatever data comes third will get written in the third location. So it will not get written in a random location. On output, information is retrieved from the control store, specifies which address to be accessed. Uh, so so there is a control information in which it is written which address is to be accessed. So as indicated, the 17th word of the control store contains the number 3, implying that the contents of data store address 3 is transferred to the output link during the outgoing time slot 17. So since it is written sequentially, so if number 3 comes 17th, then 17th, in the 17th slot only number 3 number frame will get written, because number 3 has come 17th in the duration. But since it is getting randomly accessed, so it will not have to, it will not get accessed in the 17th turn. So as indicated, the 17th word of the control store contains the number 3, implying that the contents of data store address 3 is transferred to the output link during outgoing time slot 17. So there is a time slot here and there is an address here. So even if it is the 3 number data, it is getting stored in the 17th address because it is getting stored sequentially. But when they are accessing, they are just reading this 3 and they are putting that in the frame. So they will know that this is the third address. So there is a control information which will indicate this is the third part of the frame, even if it is in the 17th location. So that's how, even if you are writing it sequentially, you don't get mismatched. Because the thing is, if this data comes in a random fashion, if the data comes in a random fashion, then they are getting stored sequentially. So what happens is, we will have a sequence like 1 5 2 3 9 4, like that. Then how to know which part of the frame was what? So we cannot have the, if the data is accessed as 1 5 2 3 4 sequentially again. So why we are not doing sequential write and sequential read? Because if we do a sequential write, then whatever data comes first, so the first slot will come first, say, then the 5th slot comes, then the 3rd slot comes, then the 4th slot comes, then the 9th slot comes, then the 7th slot comes, like that it is coming. So they are getting stored like this only. So the 1 is getting stored in the first slot, but 5 is getting stored in the second slot. Okay, so 5 is getting stored in the second memory slot. Here it is memory slot, and here it is data. So 5 is getting stored in the second memory slot, and 3 is getting stored in the third memory slot, but 9 is getting stored in the fifth memory slot. So if you, because this is written sequentially, now if you read them sequentially, what will happen is that you will read 1, then you will read 5, then you will read 3. So that is not done, because then your data will get jumbled up at the output. So what you will do is, you will access 1, then you will search and you will access 3, then you will access 4, then you will access 5. So like that. So you are accessing in the order of the data. When you are reading, you are accessing in the order of the data, not in the order of the address. So you are not accessing readings sequentially, even if you are writing sequentially. Or you can do the opposite. You can write randomly. If you write randomly, then what will happen? The opposite of this, that is the second mode of operation. In the second mode of operation, there is a RAM. So 1 2 3 4 5, these are the memory slots. Okay, so if you write randomly, 1 will come in 1, the next packet is coming as 5, so 5 will be written here, not here, because we are writing randomly. This is writing randomly. So if you write randomly, then all the addresses will match with the memory slots. So I mean, not address, rather slot number. All the slot number of the frame, all the subframes will match with the memory slot, like this. So when you are reading, what you will do is, you will just read sequentially, because all the slots are matching. So if you read like this, the frame is already constructed. So read sequentially. So if you write randomly, you have to read sequentially. If you read randomly, you have to write sequentially. You cannot do both random or both sequential. Is this concept clear? Okay, so next, this is purely time switching. That means all the data is getting stored and then they are getting outputted according to their time slots. Now, what is the disadvantage of this time switching? If you have a lot of data, then your data might have to wait for a long time, because as I said, your entire data will not get transmitted at once. Say one part of your frame is getting transmitted, then you have to wait for 100 other users to transmit, then you will again get a turn to transmit the second frame. So that is not fair. That means you have to wait for a lot of users. So so since there is only one time division channel, so you will have to wait for a lot of time. So we have to add some kind of a compromise between space division switching and time division switching. Space division switching has the disadvantage that you need a lot of connection, because in space division switching you need as many paths as there are links. So if you have n input, m output, then you need n into m connections. So that is a disadvantage. But what is the advantage? Since all the dedicated links for users are made, so you don't have to wait for the links to be get made. You can directly start transmitting, because there are dedicated links for every pair. So whenever one person wants to transmit to another person, they will just use their own dedicated path. So that is the advantage and disadvantage of space switching. But when it comes to time switching, the opposite happens. When it comes to time switching, so in space switching, what is the pro? The pro is that it has minimum latency as switches have dedicated connection. Now, what is the disadvantage or con? Con is that lots of cross points need to be made. Exactly how many? Lots is not a very scientific word. So exactly how many? N into M. Now we come to time switching. And time switching has the exact opposite pros and cons. Pro is that you don't need lots of hardware. Only memory is needed, which is cheaper, cheaper than cross points. So it is cheaper than cross points. So it is cheaper to implement. Making a lot of cross points is not convenient. And what is the con? The con is that users have to wait for a long time if number of users is large. If number of active users is large. So you have pros and cons of space switching and time switching. So now what we will do is we will have a multiple stage switching. So now we will come to multi-stage switching, where we will use both space switching and time switching so that we can get a compromise solution which is not as expensive to implement as space switching, but not as high on latency as time switching. Okay, so that is the two-dimensional switching. So that is called a time-space switching. So this is a two-stage switcher that is called time-space switching. And then there will be three-space switching, three-stage switching, and that will be called space-time-space switching, and another three-stage switching which is called time-space-time switching. So we will have ST switch, TST switch, and STS switch as the next topics. So first coming to a TS switch or ST switch, this is called a time space switch. So in time space switch, what happens is you have you have some cross points. So if you have n users, you have n cross n cross points, but each user, so if you have some this cross points, but each user's data is again transmitted using a time slot multiplexing. So there is time slot multiplexing as well as a space multiplexing. So there is this space stage will have a form dedicated links, but since there is time space switching, so if each of these time space switches have k channels, okay, bear with me. So if each of these time stage switches have k channels, then you are serving n cross n, right? So each of them, if they have k, then you can actually serve n cross k switch users, because each of them will have k users again. So k users are getting time multiplexed, and then that is multiplied by n at the space stage. So instead of only serving n cross n, if this was a purely space switching, then you could have served only n square, n into n, right? N users. So you can have n square connections. Here you can have n into k connections, n into k users, active users, because you have each cross point switch input side will have k time slots for time division multiplexing. So that is called a space time switching. So, and this entire thing is connected by a control. So there is a control for time division multiplexing, and then there is a control for space division multiplexing also. So there are two control stages. Now we will be analyzing the implementation complexity. So here implementation complexity means what is the expense of implementing such a switch. Now for a space division switching, the cost is in terms of number of cross points we have to build. So in space division switching, the cost is basically the number of cross points that we have to build. But in time division switching, what is the cost? The cost is the buffer size, the RAM that we have in time division switching, right? This RAM, this RAM, this RAM will have a cost. So larger, so if you have more time slots, if you are serving more users, then you will have more time slots. If you have more time slots, you will need to store more. So you will need more RAM. So the cost is memory. And in space division switching, the cost is cross points. If there are n users, then there will be n cross n cross points. So now cross points are, so time division switching, time division switching, time switching is equal to memory, space switching is equal to cross points. Now cross points are, it is hypothecated that cross points are 100 times more expensive to make than memory. Cross points are 100 times more costly than memory. So this was the implementation cost when the book was written. Now memory has gotten insanely cheap. So like you can buy for 3-4 thousand, you can buy solid state drives of 1 TB, right? So memory has gone insanely cheap. So that's why cross points are no longer even 100 times. They're even more than 1,000 times costlier to make than memory. So because memory is very cheap. But since the time the book was written in the 80s, so in then cross was points were considered 100 times more costly than implementing memory. So implementation complexity is simply the number of cross equivalent complex cross points that you have to make. Implementation complexity is the number of equivalent cross points. What do you mean by equivalent cross points? So in equivalent cross points, we will of course have the actual cross points is equal to number of actual cross points. Of course, that will be a factor. Number of actual cross points, and another factor will be memory size. But memory is not as costly as cross point. It is 1/100th of a cross point. So the cost will be memory size divided by 100. So number of actual cross points plus memory size divided by 100. That is the implementation complexity in terms of the number of equivalent cross points. So this is a very important formula. Equivalent cross points means number of actual cross points plus memory size divided by 100. So that is that. Now we will go on to the yes. So now we will be discussing the implementation complexity. So implementation complexity of this time space switch. So the implementation complexity of time space switch will have two parts. One is the number of cross points and another is the number of bits of memory, the memory size divided by 100, because memory is 100 times cheaper. Now this memory has multiple parts, which we will understand with the help of this example. So, determine the implementation complexity of a time-space switch shown in figure 5.19. So, figure 5.19 is this one. So, the time-space switch, there is a time stage followed by a n cross n space stage, where n is the number of inputs. So, determine the implementation complexity of the time space switch shown in figure 5.19, where the number of TDM input lines, that is the number of inputs, is 80. Assume each input line contains a single DS1 signal. That means it has 24 channels and each bit is and 24 channels. So 8-bit information will be transmitted across 24 channels. So furthermore, assume a one-stage matrix is used for space stage. So one-stage matrix means n cross n cross points. If there were three-stage matrices, previously in the previous week it was discussed, if there were three-stage cross points, three-stage space division cross points, then you will have a different formula that is usually proportional to n by n whole n by k whole square, where k is the number of intermediate stage switches, but we will be not going into that here. Here it is a one stage matrix used in the space stage. So the number of actual cross points, that is the number of cross points used in the space stage, the number of cross points used in the space stage, number of actual cross points, because in time division you don't have any cross point, so you just divide the memory by 100 to get the number of equivalent cross points. So but in space stage you have actual cross points. So space stage, number of cross points in space stage is equal to 80. So there are 80 input lines. So it will just be 80 into 80. Like that. So it will have 6400 cross points. Now The cross points of the on the main diagonal are included since two channels within a singularity. So that now we will determine the memory part, that is in the TDM, and there is another memory part that will be in the space division multiplexing also, because if you can see in this diagram, in the time division multiplexing there is of course memory involved, but in the space division multiplexing also there is a buffer memory involved, which is called the control store. So this control store controls the flow of data, and we need this because we do not have dedicated connection. So we do not have dedicated connection for the users. So to route the user to the to the correct data, we need a control store. We cannot rely purely on cross points. So this control store of the space stage will be one part of the memory, and the RAM used in the time stage will be another part of the memory. So there are two parts of the memory. So the number of memory bits from the space stage is determined as number of links. So there are 80 links. Number of control words. So number of control words means how many channels are there. Control word here simply means how many channels are there. So there are 24 channels. So number of control words will be 24. And number of bits per control word. Number of bits per control word will be basically just 24. How many bits do you need to represent 24 possibilities? So if there are 24 possibilities, how many bits do you need? So 2 to the power 5 is 32. So here number of bits, yeah, so number of bits per control word 824. So, sorry, number of control words used in the space, since in the space stage there are n switches, so number of control words will be simply proportional to that. So number of control words will be how many bits you need to represent these n switches. So there will be log base 2 into capital N, 80. Now log base 2 80 we will not use directly. So memory size is now space stage memory, space stage control memory size, space stage control memory size. This so space stage control memory size is simply the number of TDM links, so 80, and then number of control words, and so 80. Now number of control words. So since there are a number of control words will be 24, and what is the number of bits that we need? That is the ceiling of log of 80. So it is the ceiling of log, not just the log, because ultimately you cannot have 4.75 bits, right? You have to take a integer. So log base to 80, 2 to the power 5 is 32, 2 to the power 6 is 64. So 2 to the power 6 is 64. So this is 6 point something. So ceiling means you have to take the next integer. So it is 18 to 24 into 7. So this is the space stage memory. Now what about the time stage memory? So the time stage memory has number of links into number of channels. So this time stage memory is again divided into two parts. One is for the control and one is for the data. So for the data, how many do you need? Number of links. So there are 80 links or 80 data sources, and each one has 24 TDM channel. And how many bits do you send? You send 8 bits. So because it's a 8-bit PCM. So 80 into 24 into 8. So this is the data storage. 80 into 24 into 8 is the data storage. This is the data storage. And another part is the control storage. The control storage is 80 into 24 into 5. So the control storage is 80 into 24 into 5. Now why is it 80 into 24 into 5? Number of links is 80 as usual. Number of control words, just like here in space division and in time division, the number of control words that you need is simply equal to the number of channels. And since there are 24 channels, So it will again be 24, and number of bits per control word. Now in the space stage, you were controlling all the 80 inputs. In the space stage, you were controlling all the 80 inputs, right? So you need log base to 80, ceiling of log base to 80 as the number of bits per control word. But here, you are controlling the time slots. You are not controlling the number of inputs. You are controlling the time slots. So it will be the ceiling of log base 2 of the number of time slots. So how many time slots are there? There are 24 channels. So 24 time slots. Since there are 24 channels, so number of bits per control word will be log base to 24 ceiling. So ceiling log base to 24, 2 to the power 4 is 16. So log base to 24 is 60. Sorry, 2 to the power 4 is 16. So log base to 24 is 4 point something. So 4 point something means when you take the ceiling, it becomes 5. So 18 to 24 into 8 plus 18 to 24 into 5. So here we have 13,440 bits. Here we have 24,960 bits. So these all bits will get added into the memory. So the total memory is 24,960 plus 13,440. And to get the complexity, you divide this by 100 to get the number of equivalent cross points. So nx, that is the number of cross points, actual cross points, plus nbx, which is the space stage memory, and nbt, which is the time stage memory. And these three are combined together to get the complexity like this. And the complexity is equivalent to 6,784 equivalent cross points. Now, you might say that, are we saving anything? So are we saving in terms of complexity? So if you used a purely space switch, you would have needed 6,400. Yeah. So if you had needed, if you have this, since there are 24 channels and there are 80 users, not 6,400, sorry, you will need 80 into 24 whole square. So 80 into 24 whole square, which is a huge number. That much amount you will need. But here, that many amount of cross points you will need. So 80 into 24 whole square. So you will need around 36 lakh switches. And here you need only 6,700 cross points. So 36 lakh cross points, 6,700 cross points. So from purely space switching or purely time switching, we are saving a lot using this space time switching. Now, then we will go to STS switching. STS switching again uses the same principle, but here we will have 3 stages. So there is a space switching, and that space switching has, though it takes n inputs and it maps them into k outputs. So even if there are n inputs, there are not n outputs, there are k outputs. And then we will have time division multiplexing, where k is the number of time division multiplexing buffers that we have. So time space memory. So this number of this number of memories is the k. So here we have k such time slot operators. So here we will have n cross k switch, and here we will have a k cross n switch. So there is 3 stages in a STS switch. One, we have a n cross k space switch. Then we have k numbers of time switches, and then we have a k cross n space switch. So here the complexity is the number of space stage cross points plus number of space stage cross points, and then we will have all the space stage control bit, time stage memory bit, and time stage control bit divided by 100. So we have, in time stage we need both memory and control, and in space stage we only need control memory. So these 3 memories that we have also added here also. You can see here we have added 3 memories. So this is one, this is the space stage control memory, this is another, this is the time stage control memory, and this is another, this is the space stage data memory. Sorry, this is the space stage control memory, and this is the space stage time stage data memory. Time stage data memory, time stage control memory, space stage control memory. So we have three parts. Here also we will have three parts: space stage control bits, time stage memory bits, and time stage control bits. And then we will divide these bits by 100 to get the equivalent cross points. Now, how many cross points are here in this switch? Anyone? Anyone in the meeting can tell how many cross points are there in this switch? Okay, we have n into k, or nk number of cross points here. So we have nk number of cross points. And 1 minute, let me just open this in a different PDF reader. Yeah, so we have nk number of cross points here. And how many cross points we have here? We also have nk cross points here. So yeah, so here we have nk, here also we have nk. So we have 2 nk cross points is there. Yeah. So we have 2 nk cross points. Now we will need to get the memories. So we have solved the cross points. So we have 2 nk cross points. So for memory, we will have space stage. First, we will have space stage control bits. So how many control bits you need in the space stage? So in the space stage, you need to control this k, right? So you will have k into the number of channels. So the number of channels is C. Say there are C channels or C time slots in the time division multiplexing. There are C channels. So here you can see in the space division switching formula, number of links. Number of links will be K, since we have K output links, small k. And what will be the number of control words? The number of control words will be the number of channels. So C. And what is the number of bits per control word? So the number of bits per control word here will be the number of links that we have. So log base to k, ceiling of log base to k. So log base to k, and here we will have a ceiling. So this one will need nk. So this one will need kc log base to k. So this one will need kc log base to k. So this one will also need kc log base to k memory, control memory. So both of them will need kc log base to k. So 2 kc log base to k. So that is the number of space stage control bits. Now number of time stage memory bits. Time stage memory bits is how many how many time stage switches do you have? K switches. You have k switches. Each of them has c channels. So kc. And each of them will transmit 8 bits at a time. So kc into 8 bits. So the number of the memory you need is kc into 8, which you have. Time stage memory is straightforward, kc into 8. So here this is simply kc into 8 bits. Now number of time stage control bits. So again, for control bits you have to see how many switches are there. K switches are there, so there will be k links, and each link will have c channels. And now you need to do the log, that is the bit per control word. This bit per control word will be different in space and time. In space it was kc log base to k. In time it will be kc log base to c, because Here you are selecting which switch to go to, right? Why is it this log base to k? Because you have k options and you have to choose one. So that is why you need log base to k bits to represent that choice. But here you have C time slots, channels. So from C channels you have to choose one. So here you need log base to C bits to represent that choice. So that's why this is KC log C and this is KC log K, space stage and time stage control switching. So you have KC log C. So 2 KC log N, sorry, not K, this will have N switches, and since N is larger, this will have, the complexity will be KC log N, not K, because N is larger. So whichever is larger, you need to provision for that, right? So sorry on my part, this will be KC log N, not KC log K, because N is larger. So this is memory size, right? So you have to get the maximum memory size. So it will be KC log N. So it is KC log N, 2 KC log N for the 2 space switches, plus KC8, which is the time stage memory bits, and time stage control bits is KC log C. So you divide that by 100 and you have number of space stage cross point as 2kn. So this will be the complexity. This is the number of equivalent cross points. And we will solve a problem on this in the assignment. And then we have TST switching. TST switching is in the STS switching we had 2 space switches, and in between the 2 space switches there was a time switch. In TST switching you have 2 time switches, or 2 layers of time switches, and in between there is a cross point switch. So here we have TDM inputs, and then these TDM inputs in the middle are connected using a cross point. So here the complexity again. So complexity is the number of cross points. So the how many cross points are here? N. So n cross n square. In the space switch we have n square cross points. Actual cross points is n square. I don't think you have any doubt here. So you will have n square cross points. Now coming to the tougher part, time switching, space stage control bits and time stage control bits and time stage memory bits. So first one is space stage control bits. So since there are n, how many inputs are there? There are n inputs and n outputs. So it will be n into how many channels are there? Say there are L channels. It is saying L time slots are there. So if there are L channels, then n L log n. Now in the time stage, whatever is required memory, you have to multiply them by 2, because there are 2 time stage switches, because it is a TST switch, time space time switch. So 2 into number of inputs is n and number of channels is c. So NC data packets can be sent, and each will be in 1 bit format. So NC into 8. So 2 into NC into 8 is the memory. And then 2 into, because there are 2 time stage switches, n into L. L is the number of time slots. N into L into log base to C, because C is the number of channels. So 2 into NL into log base to C. So this will be the TST complexity. So so it has been seen that STS and TST, this is the STS complexity curve, this line, this zagged line, and this straight line is the TST complexity curve. As you can see, the STS complexity curve increases with the utilization of input channel, that is the traffic. As traffic increases, as the traffic load increases, STS complexity increases linearly. But as traffic increases, the TST complexity remains mostly constant. It does not increase that much. So as much as STS. So in low traffic, we should use STS, because there are two. In low traffic, we should use STS. But as in STS we have 2 space division switches. So when we have high traffic, the number of cross points needed is very high. So the STS complexity goes up, whereas the TST complexity remains low. Now there is TSSST, but we don't need that. We will end our discussion in SSSTS and TST. That will be good enough for us. Okay, so now we will be moving on to assignments. So how many bits and time slots does T1 frame consist? So T1 is a particular type of frame that is used in PCM. So you have 192 bits. Let me open it in a different PDF reader. Okay. So T1 frame is a kind of standard frame. T1 frame is a kind of standard frame. This is a T1 frame. So it will have 192 bits in groups of 8. So 8 bits, that is 1 byte like that. So in groups of 8, it will have 192 bits, and it will also have one sync bit. This is called a sync bit. Okay, so this is a sync bit. So ultimately we have 193 bits. And 192, if you divide by 8, you have 24 time slots. Each of this is a time slot. This is a time slot. This is another time slot. This is another time slot. Like that. So there are 24 time slots. So the correct answer is 193 and 24. Option B. Now question number 2. Calculate the maximum access time that can be permitted for data and control memories in a TSI switch with a single input and output trunk multiplexing 1000 channels. So in a time slot interchange switch, there are 1000 channels. Now there are 125 frames. The one frame is of 125 microsecond duration, right? So if one frame is of 125 microsecond duration, so there are 1000 channels. So in that 1000 channels, you have to perform, in that frame itself, you have to perform 1000 reads and 1000 writes. So if there are 1000 channels and we want to send one frame of 125 microsecond duration, so this is of 125 microseconds, so there are 1000 channels. So of course we will, since there are 1000 channels, means we can send 1000 data together, 1000 time slot data together. So since we can send 1000 packets together, we will divide the frame into 1000 packets. So each packet needs to be read, each packet needs to be written. So 1000 packets each needing one read. Whoever has the mic on, please turn it off. Noise is coming. Each needing one read and one write. Each needing one read and one write. So you need 2 into access time. So if one read needs TC time, one read takes a TC time, T time, TC, let's say TC. So you need 2 TC time for each packet, right? 2 TC time for each packet. For each packet. So total time needed is 2 TC into 1000. 2 TC into 1000. And this 2 TC into 1000 should be equal to 125 microseconds. So the TC, or the access time, TC itself is the access time. Access time equal to TC is equal to 125 by 2000 microsecond. So this will come to be 0.625 or 62.5 nanosecond. 62.5 nanosecond. So that is the answer, 62.5 nanosecond. So answer is option C. Now in question 3, calculate the access time of the memory modules in parallel in and serial out time switch using 64 input and 64 output streams, with each stream multiplex 32 channels. So there are 32 channels and 64 output streams. So access time of the memory modules is, so there are 64 inputs and 32 channels. So you will, for 64 inputs, you need to read them. 64 inputs require. Now this is a parallel in, serial out. See, so 64 inputs require 64 reads because parallel in, right? So all the data is coming together because it is parallel in. Parallel in. So all the required needs, all the data needs reads together, 64 reads. But one write. Why? Because it is a serial out. So data will come out one by one. So in one cycle you just need one write. So you need one write because it is a serial out. So 64 reads and one write. So you total need 65 cycles, right? 65 total, therefore 65 memory cycles needed. So the access time is the duration of one memory cycle, which is TC. So 65, now there are 32 channels. So 32 such data streams will be there. So 32 into 65. 32 into 65 cycles will be needed, and each cycle lasts TC. Now this 32 into 65 into TC must fit into the frame time. So total frame time 125 microseconds. So everything that happens must happen within 125 microseconds. That is the frame duration. So TC is equal to 125 by 32 into 65 microsecond. So this comes to be around 60 nanoseconds. This is 60 nanoseconds. Now, in a TSI switch, the number of time slots or samples per frame in the input stream and in the output stream can be denoted by N1 and N2 respectively. The access time in the switch can be represented as. So, here it is said that the TSI switch has number of samples per frame in the input and output stream as N1 and N2. So, sorry, yeah, so basically in the TSI switch there are N1 input streams and N2 output streams. So 125 by N1 plus N2 microseconds you will need. So there is nothing much to study here. So you have N1 times N1 samples here and N2 samples there. So what will be the total time needed? So N1 samples here and N2 samples here. So 125 by N1 plus N2. So it is straightforward. Because 125 microsecond is the total sample frame duration. So next question. Now consider a 32 cross 32 time switch which is multiplexed with 8-bit PCM encoded voice signal. How much storage is needed to construct such a switch? So 32 by 32 time switch which is multiplexed with a 8-bit PCM encoded voice signal. So you are sending a normal 8-bit signal, PCM signal, and there is a TDM switch. There is a TDM switch. So let's do it here. So there is a TDM switch. So there are n inputs and n outputs. TDM. So if there are n inputs and n outputs, so 32 cross 32. So here n is equal to 32. Now each of them is carrying a PCM. Each of these lines are carrying a PCM signal. So PCM. So the data storage required is, so data storage required is 32 into 8, because each of them is carrying a PCM signal of 8 bits. 32 into 8. So 256 bits. Now this is the data storage, easier part. But what is the control storage? For the control storage, you need how many links are there, of course, and you are controlling this 32. Now you have to control these 32 slots, right? So to control these 32 slots, to choose which slot to use from these 32 slots, you need how much data? You need log base to 32 data. Log base to 32 bits. Silly. So you need log base to 32 bits. So you need 32 for control storage. You need 32 by 32 into 32 control words, and each control word will be of log base to 32 bits. So 32 into 5, 160 bits, because log 32 is 5. Therefore total storage is equal to 160 plus 256 bits is equal to 416 bits. Now, so the correct answer will be 416, option A. Next is, consider a time switch where the number of TDM input lines is 100. Assume each input line contains a single DS1 channel. So single DS1 signal, that is 24 channels. Now furthermore, assume a one-stage matrix is used for the space stage. Crosspoint cost is 100 times the cost of a memory bit. What is the implementation complexity of such a time space switch? So this is a TS switch, time space switch, like I have taught just now. So in this time space switch, you just have to find the implementation complexity. So I will be putting this question here, and this, yeah. So here we have to just follow this part, time space switch implementation complexity, like we have discussed. We have to just follow that here. This one, we just have to follow this one. So number of cross points, first we will multiply and get and then we will get the control stage bits, and then we will get the space stage control bits, then we'll get the time stage data bits, then the space stage control bits, time stage control bits. So uh, yeah, so why don't you follow this and try? So I will give you some time. The correct answer is B. So the the correct answer is B. Why don't you follow this and try to get the correct answer? Mm. In 2 minutes, I will come back and check. Okay. So I will keep it here. Yeah. Okay. Okay. So we will now go on to the solution. So here, first we need to find the number of actual cross points. So the number of actual cross points will be, let's do it here. So the you can just follow here. The number of actual cross points is, since there are 100 inputs, there will be 100 into 100. Number of cross points is 100 into 100. So here it's 10 to the power 4. Now, control stage memory bits, space stage control bits, space stage control bits. This is basically the number of inputs, that is number of inputs is 100 into the number of channels. So how many channels you have? 24 into log base to 100 ceiling. Because you have 100 outputs, so you have 100 switches, 100 choices. So you need a 100-bit word, sorry, log base to 100-bit word to represent your choices. So this will come out to be 16,800. Next is memory time stage memory bits. This is just 100 into 24 into 8, because there is a 8-bit PCM. And The time stage control bit will be time stage control bits is 100 into 24 into number of channels, because in TTM the choice is in the channels, so of course the log will be in the channel. So if you add all these three together, you will get something like 48000, all these three together. So the complexity will be 10 to the power 4 plus 48000 by 100. So 10,480 will be the complexity. Now next, so here the answer is 10,480. Next is STS switch. Again we have to do time complexity analysis, but this time for a implementation complexity analysis for a STS switch. So here you have 7 center stage time switches implemented over 16 TDM links with 128 channels on each link. Assume that a cross point cost is 100 times the cost of a memory bit. So how many cross points do you need? Actual cross points. Number of actual cross points is number of actual cross points. Here you have, this is an STS switch, space time space switch. So you have two space switches. Each will have n cross k, where k is the number of channels, n cross k. So n is 16 TDM links. So there will be 16 users, 16 TDM links. So n is 16 and k is 7. So 2 into 7 into 16. So 224. Now we need the memories. Space stage control bit. Space stage control bit is number of TDM links, which is n. N is 16. So you just did n 16 into number of channels, which is number of channels is 7. Sorry, number of channels is 128. So and this will be log base to 16. Okay, so this is not 2, this is 2 into 7. Why 2? Because, and there will be 7 because there are k switches. So 7, 2 into 7 into log base to 16. So this will be around 7168. Now time stage memory is simply 7 into 128 into 8. So this will be 7168. So why 8? Because 8-bit PCM and there are 128 channels and there are 7 such time stage switches. So 7 into 128 into 8. And the time stage control bits. So that will be 7 into 128 into log base to 128. So here the number of channels will come into play. So time stage control bits is 7 into 128 into log base to 128. So this will be 6272. Now if you add all these three, you will get 7168 plus 6272. 7168 plus 7168 plus 6272. 20,608. So here you will need 20,608 bits of memory. 20,608 bits memory. So if you need 20,608 bits of memory, what is the complexity? Complexity is simply memory by number of cross points plus memory by 100. So number of cross points is 224 and memory by 100. Memory is 20,608 bits. So you divide by 100. And finally you will get the implementation complexity to be 430. Now you repeat the same, but this time there will be a TST switch, time space time switch. So the other things remaining same. So we have 25 space stage time slots and 16 TDM links and 128 channels per link. So the input is 16. So N is simply 16. K is 25 and C is 128. So number of cross points is 16 square, 256. Here you only have one space switch, TST. So there is no 2 here. And space stage control bits. Space stage control bit will be N into K into log N instead of log N. So here this will be 1600. Now time stage control. This will be similar, but 16 into 25 into log base to 25. So this we have to take the ceiling because log base to 25 is not a perfect integer, but we need a perfect integer. So this will be, and since there are two time stage switches because these are TST, so 2 will be multiplied here. So 2 into 16 into 25 into ceiling log base to 25. Sorry, not 25. There are 128 channels, so log base to 128. So this will be 5600. And time stage data storage, time stage data is 2. There are 2, 16, 25 and 8 because there are 8 bits. So this will be 32768. Now add these three together. These three are the memory. Add these three together. So memory is equal to memory will be 43200. If you add these three, 32,768, 5,600 and 600, 1600. You get, no, not here. I think the answer is slightly wrong here. It will be 32,768 plus plus 5,600 plus 1600. 32,768 plus 5,600 plus 1600. So memory will be Uh, 39,968. So it will be not be 43,200. It will be 39,968. So implementation complexity will be number of cross points that we have used. Implementation complexity is the number of cross points that we have used, that is 256 plus 39,968 divided by 100, memory by 100. So 399.68 is 400, so this will be 656. So this will be 656. Correct answer is B. Now TST switch becomes more cost effective than an STS switch. So let's go back to the graph. This is something that just you have to see the graph and get, because you cannot predict this. So you just see the graph and you see that when does STS become more advantageous? Sorry, not STS, TST I think. When does TST become more advantageous? TST becomes more advantageous where the number of input channels, the utilization of input channels is low. So in low traffic scenario, low channel utilization, TST becomes low. Sorry, in low channel utilization, TST has a higher complexity, but in high channel utilization, TST retains it. It does not increase that much as STS. So TST is better. So high channel utilization. The correct answer is high. In high channel utilization, TST is effective. It has a lower complexity as compared to STS. In high channel or utilization scenarios, TST has a lower complexity as compared to STS. Now, an elastic store can compensate for long-term instabilities that can produce arbitrary differences in the amounts of data transmitted and received. So, what is an elastic store? An elastic store is a small buffer. An elastic store is a small buffer used to store data from different sources if they come at different rates in order to synchronize them. So elastic store is a small buffer. So like if you have data coming from two links, one is nearly 100 GB, 100 Mbps, another is 1 Mbps. So of course, if you have two data sets, then one is of 100 Mbps and one is of 10 Mbps. Then of course the 100 Mbps data source will complete transmitting its data a lot faster than the 10 Mbps data source. So one has completed transmitting data, another has not even finished transmitting half of its data. So in that case, there will be a lot of synchronization problems because one has completed the data and another has not yet given the data. So what will happen is that 100 bits, 100 Mbps source, those data the data that is coming from the 100 Mbps store, they will be temporarily stored in an elastic store till the 10 Mbps data finishes transmitting completely. So then you have both data sets and then you can go on with the processing. So this difference in arrival time of different packets causes a phenomena which is called jitter. Jitter, jitter. So difference of time due to arrival of packets will cause jitter. Now to prevent this jitter, we will use an elastic store. But that this elastic store is for short-term instabilities. As I have stated, it is a small buffer. So a small buffer cannot hold a lot of long-term data. So it cannot solve arbitrary differences in amount of data transmitted and received. That is the data rate difference. It cannot solve that data rate difference for problem for long term. It can solve that data rate difference problem exactly, but only for short term because it is a small storage. So while this statement is mostly true, it will not be long term. It will be short term. So the statement that is given here, long-term instabilities, is false. So that concludes our session today. So we solved 10 problems on space and time switching. And next week onwards, we will be moving on to the interesting part, which is traffic analysis and Poisson traffic and all. So don't miss that. And if you have any doubt, my email is I think not provided to you. If not, then if you have any doubt, you can just write in the message board of the NPTEL. If you have any doubt regarding the class, please write in the message board of the NPTEL, and I will be promptly answering that. So thank you. With that, I will be ending the meeting. Okay. Yeah. हेलो। हाँ, तुम कहाँ हो? मैं अभी निकल सकता हूँ। अच्छा अच्छा अच्छा, काम हो गया है? बट तुम लोगों को रुकना पड़ेगा अभी, तुम लोगों का काम हो गया है तो चलो। हाँ फिर सुनो ना, सौरभ को थोड़ा बोल दो ना, मेरा मेरा टेलर के पास एक पैंट है, थोड़ा ले लेने को, फिर मेरे को मिला। हाँ, अरे मेरा पैकेट में मेरा नाम लिखा है। पैकेट में मेरा नाम लिखा है। वो बीच वाला टेलर, भंजो टेलर, जो दाढ़ी वाला एक बैठता है ना, जिसमें। दाढ़ी वाला जिसमें बैठता है, मुसलमान जिसमें बैठता है, वो सब बीच वाला टेबल, उसके पास मेरा पैकेट नाम का पैकेट है, वो थोड़ा उठा देना बस। ठीक। हाँ हाँ ठीक।